Now, why are the Pearson distributions so important? So these are the Pearson distributions. Why are they important? Now this plot may look complicated, but let's just go through some of the key features of it. What I've got on the horizontal axis here is the skewness of the distribution. So if a distribution has a long tail to the right or left, then the more skewed it is, the more you go out on this axis. This axis here is the kurtosis of the distribution. That is, how fat-tailed is it? Okay. So distributions along this axis are symmetric. They don't have any skewness at all. So you can see the uniform distribution is symmetric. The normal distribution is on this axis. All of the student t distributions are on this axis, okay, because they're symmetric. But as you go down here, these distributions get fatter and fatter tails. All right. The uniform has almost no tails. The normal distribution has relatively short tails among the families of distributions. Here's the logistic distribution, and then student t's with 6, 5, 4 degrees of freedom go down here to a standardized kurtosis of 10, and then you could even go to infinity. The Cauchy distribution is a student t distribution with 1 degree of freedom. Its tails are so fat the distribution doesn't even have a mean or a variance, and that is infinite on this scale. But the important feature of the Pearson distributions, the key feature, is that if you pick a plot anywhere on this chart, suppose you picked a point right there and said, my kurtosis is 4 and my I'm sorry, my kurtosis is 7 and my skewness is 4. Suppose you pick that point on the plot. And if you pick a point on this plot, the key thing here, if you pick a point on this plot, there is a Pearson distribution that can represent that point. And that's true for every point on this plot. No matter where you are on this plot, in terms of skewness and kurtosis, there exists a Pearson distribution that can represent that point exactly. And that's why the Pearson distributions are so famous, okay? So, but there are some limitations here, and I'll talk about what those limitations are. But one of those, for example, this is the area of the beta distributions, right? And if you're in this area, you've got a beta distribution, and that is bounded. But if you wanted something with infinite tails, there's no Pearson distribution that would provide that. Anyway, that's why the Pearson distributions are important. Now, where do Pearson distributions fit in the overall history of probability? Well, I don't know how far you want to go back, but the first publication on the normal distribution was by a Frenchman named de Moivre in 1756. He first published the normal distribution as the limiting case of the binomial. And just about the same time, interestingly, Bayes and further developed by Laplace published his paper posthumously and basically laid the groundwork that probabilities can be of any shape, including whatever might be the shape of your data or the shape of your opinions or beliefs. And these are two completely different views of the world. This one led to the whole world of classical statistics and frequentist statistics. This has led to Bayesian statistics, including decision analysis, where you can actually use expert opinion to help you assess probabilities. The next big thing that happened around the 1900s in the classical statistics world is the Pearson distributions were developed. Where we are today is in a very awkward situation where most people never learned about the metalogs in school. They learned about the Pearson distributions, or some of them, but they're trying to apply them up here where you have partial data, you have partial states of information, you have belief-based, and they're never developed for that, and they don't fit it very well. The next thing that happened, I think, and you can tell me that I'm biased and, you know, blah, 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 but I think that the next really big thing that happened is now we have the metalog distributions that actually can be used in either domain with equal facility. And they're more flexible and easier to use and simpler equations than are the Pearson distributions. So we might as well use them as long as better technology is available, or at least have them available as an arrow in your quiver.